Good morning everyone. So, we will be starting with our next separation process. It is the centrifugal separation process, and this will be used whenever you will be you will require to separate the slurries from solid particles from liquid. So, they are not completely soluble, they are called slurries. When the suspended materials or the solid materials are there in the liquid, so it is called a slurry. And in order to of sizable size, for example, they are of the size of the microns and so on and so forth, and whenever you will be applying a centrifugal force, these particles will be subjected to a body force which is nothing but a centrifugal force omega square g sort of thing, and they will be pushed towards the wall of the container, and it will be entirely depending on the density of this particle. So, heavier particles will be pushed more towards the wall. So, if you have a slurry of heavier and lighter materials, the heavier particles will be pushed towards the walls and they can be separated out from the wall. So, in centrifugal separation processes, the main driving force is centrifugal force. The driving force is centrifugal force that induces separation, and it will be something like this. This process can be described by the schematic. So, this is the slurry feed will be going into the system, and this the middle shaft will be rotating and the whole system will be rotating, and solid particles experience a force directed towards the wall. Because of this rotation, solid particles in the slurry they experience a force, there is a centrifugal force towards the wall. Okay. Now, there are this centrifugal separation can be operated on two systems. One is the solid liquid system, that is a slurry system. Second one is liquid system, where the two liquids will be having a difference in density. So, therefore, it is not necessary that the centrifugal separation process can be operated on solid liquid system only. It can operate on a liquid system as well if there is a density difference of the two liquids that we are talking about. Okay. So, for a slurry feed, you will be having the bowl will be rotating about the central axis with a speed omega, and this slurry will be coming, and the solid particles will be experiencing a force. So, centrifugal force towards the wall. So, therefore, they will be depositing over the walls. Okay. So, you will be getting a layer of solid particles there, and these will be the liquid, okay, and you will be having solid particles there. Now, these solid particles can be separated out. In case of liquid system, and we are talking of two liquids, one is heavier, another is lighter. Now, the heavier liquid that will be having higher density, it will be pushed towards the wall, and they will be existing close to the wall, and you will be having the another liquid to the other side. So, you will be having a heavier liquid towards the wall. So, this is nothing but a heavier liquid having higher density, and this will be the lighter liquid. So, the heavier liquid can be taken out from the wall and the centrifugal separation process will be effected in this system. Okay. So, we can have either a solid liquid system or we can have a liquid liquid system of different densities as well. Now, let us look into the principle of centrifugal separation process. It acts, let us say, centrifugal force acting on a particle of mass m located at a radial distance r from the center. The force is represented by F c is equal to m omega square r. Okay. The angular velocity is related to the linear velocity by the relation where omega is the m is the mass, omega is the angular velocity, r is the radial distance, and angular velocity omega is related to linear velocity as omega is equal to v by r. Now, if you have a rotating speed in revolution per minute RPM, okay, RPM is nothing but the revolution per minute, rotating speed in this is RPM, okay, revolution per minute, then omega, the angular velocity, is given as 2 pi n divided by 60. Okay. So, it is rotation per minute. So, 60 is to convert into per second, and one full rotation or full revolution means 2 pi radian. Okay. So, this angular velocity will be radian per second. Okay. Then the centrifugal force in Newton can be calculated at as F c will be nothing but m into 4 pi square n square divided by 3600 times r, and this turns out to be 0.01097 m times r n square. Okay. So, this is in the unit is Newton, the unit of the centrifugal force. So, on the other hand, if you compare this centrifugal force with the gravitational force, the then we can see how much more the centrifugal force is compared to the gravitational force. Now, gravitational force working on a mass m is given as f of g is nothing but m times g. The ratio of centrifugal to gravitational force then can be computed. Ratio of centrifugal to gravitational force can thus be computed. F c by f g is equal to r omega square divided by g. So, it will be r over g, replace the expression of omega, that is 2 pi n over 60 square of that. So, it turns out to be 0.00118 r n square. Now, in this expression we put g is equal to about 10, it is 9.8. So, we put it about 10 meter per second square. Thus, the force developed in the centrifuge is r omega square by g times that of the gravity. Okay. So, this is expressed now. So, centrifugal. So, by this ratio, what you can say that centrifugal force is this many times more than g or the gravitational force. Okay. So, how it is expressed now? It is expressed as we give an example. If we talk about a radius of centrifuge bowl, radius of centrifuge bowl, if that is 0.1016 meter, and if you talk about a rotational speed about 1000 rpm, okay, revolution per minute, then Fc by Fg becomes okay, I will put the value Fc by Fg becomes 0.00111 r n square. Put the value of r, put the value of n, square of that. So, it turns out to be 130.6. So, that means we term that centrifugal force is 103.6 times gravitational force. Okay. And it is expressed as that, as if this whole statement is equivalent to 113.6 g. Okay, that is the nomenclature. So, if generally sometimes you will see that the centrifuge is operating at 5 g, at 10 g, that means it is 10 times the gravitational, the centrifugal force that is generated is 10 times the gravitational force. If your centrifuge is operating at 20 g, 20 g means the centrifugal force that will be generated, it is 20 times more than the gravitational force. Okay. So, if your r becomes 0.2032, then Fc by Fg will be 227.2, and we will call that centrifugal force generated is 227.2 g. That means centrifugal force generated is 227.2 times more than the 2 times the gravitational force. Okay. So, that is the nomenclature. Sometimes whenever you will be looking into the specification that is written on the wall of the centrifuge, you will see all these informations. So, that means the centrifugal force generated x times the gravitational force. Okay. Now, let us look into the settling rates in centrifuge. Now, we are talking about, let us say, talking about a slurry system. And what is a slurry system? It is basically solid liquid system. Okay. In that, so let us first draw a typical centrifuge. So, we draw a schematic of a centrifuge, then all our nomenclature will be fixed. Okay. So, we are having the liquid surface and the whole system is rotating about its central axis with omega. Okay. So, the height of the centrifuge is b, and let us say this distance is r2. Okay. So, r2 is nothing but the radius of cylindrical centrifuge. Okay. Let us say this distance is r1. So, r1 is the radius where the liquid surface is located. So, this is nothing but the liquid surface. Liquid surface is located, and Rb, let us say Rb is any location of a solid particle. Rb is location of a solid particle, okay, at any point of time, let us say, and the feed is going like this. So, you are feeding the slurry from the bottom, a whole thing is rotating, and typical trajectory of a particle will be something like this. This is a typical trajectory of a particle. It is a parabolic in nature, trajectory of a particle, of a solid particle. Okay. Now, at the end of the residence time, particle is at a distance r b from the axis of rotation. R b is location of the solid particle at the end of residence time. Okay. What is the residence time? Residence time is total flow rate. The feed is being fed into the centrifuge at a particular flow rate, let us say that is q meter cube per second. Okay. And you have a certain volume of the centrifuge. So, let us say that is v meter cube. So, the residence time is nothing but v by q. Okay. So, that is the average residence time of a particle that will be staying within the centrifuge. Now, if RB is less than the R2, the wall, the radius of the centrifuge, the particle will be going away. It will not be settling on the wall; it will be going away in the product stream. So, there will be no separation. So, our objective should be the flow rate should be maintained such that RB, that is the location of the particle at the end of the residence time, must be less than R2. So, that it will be hitting the wall and staying there. Okay, then only the separation will be possible. That means, if RB is less than R2, then particle leaves the bowl, leaves the centrifuge with liquid. Okay. If RB is equal to R2 or greater than R2, it will be equal to R2, it cannot be greater than R2 because there is a physical limit. Okay. If it is equal to R2, then it deposits, it gets deposited on the wall. Once it gets deposited on the wall, it will be effectively separated from the liquid. Now, in a Stokes law regime, what is a Stokes law regime? When the Reynolds number is less than 0.1, that is called the Stokes law regime. And what this Reynolds number will be defined on the diameter of the particle, and the diameter of the particle will be extremely small, in the order of micron, and so it will be really small. The terminal velocity can be expressed as terminal velocity in gravitational field becomes Vt is nothing but g times dp square. Dp is the particle diameter, 18 mu into rho p minus rho. So, g is acceleration due to gravity, 10 meter per second square. Dp is diameter of the particle diameter. Mu is water viscosity or fluid viscosity. Rho p is particle density. And rho is water or the fluid density, whatever we are dealing with. Okay. This is the expression of terminal velocity under the gravitational field, but in the centrifugal fields the terminal velocity becomes under centrifugal force. The expression of terminal velocity is different. The terminal velocity, the g will be replaced by the omega square r. Okay, g will be replaced by the omega square r, and this terminal velocity becomes omega square r dp square rho p minus rho divided by 18 mu. So, that is the terminal velocity under the centrifugal force, and compared to the gravitational force, the g will be replaced by the omega square r. So, acceleration due to gravity will be replaced by the centrifugal acceleration. Okay. Now, this terminal velocity is nothing but dr dt. Okay, if you look into the definition of velocity, that is nothing but dr dt, and acceleration is dv dt. Okay. So, therefore, this expression can be written as dr dt, that is the location at any point of time, omega square r divided by 18 mu dp square times rho p minus rho. Okay. Now, you can integrate it out. If you integrate it out, so it becomes, you just separate the variables, dt equal to 18 mu divided by omega square rho p minus rho dp square integral dr by r, and this will be, let us say, from r1 to r2, okay, from 0 to t terminal. Now, this will give you an expression of the time t or the terminal, the time becomes 18 mu divided by omega square rho p minus rho dp square ln r2 by r1. Okay. Now, if the volumetric flow rate becomes q and V is the volume of the liquid column in the centrifuge, okay, if V is volume of centrifuge, volume of liquid column in centrifuge. So, in fact, there will be two phases in the centrifuge, one will be the liquid phase, another will be the solid phase, and the solid phase volume will be the solid particle that will be residing on the wall, but that volume will be extremely small compared to the volume of the centrifuge. So, volume of the liquid. So, volume of the liquid will be roughly equal to the volume of the centrifuge, okay. And Q is the flow rate, steady state flow rate of the liquid, So, residence time is nothing but, as I told earlier, it will be V by Q. So, it will, and this becomes okay. So, now you can combine these two, and Q becomes v by Q. So, you just replace T by T in the as V by Q in the above expression, the earlier expression. This becomes 18 mu divided by omega square rho p minus rho dp square ln r2 by r1. Okay. And what is the value of volume? Volume becomes nothing but pi times b r2 square minus r1 square. Okay. So, Q, the expression of Q is nothing but omega square rho p minus rho dp square 18 mu ln r2 by r1 multiplied by pi b r2 square minus r1 square. Okay. What I was saying, that this r1 will be very small. So, it becomes the radius of the centrifuge itself. So, the condition for this is nothing, the flow rate should be matched by, should be given by this expression. Okay. Now, particles with diameter smaller than dp calculated from this equation will not reach the wall. So, the conclusion is, the interpretation is, particle of diameter less than, smaller than dp calculated from above equation. So, what is the expression of dp? dp will be nothing but q times 18 mu ln r2 by r1 divided by omega square rho p minus rho times pi b r2 square minus r1 square, okay, raised to the power 1 upon 2. So, if particle of diameter less than dp calculated from this equation, then they will not reach the wall. of the bowl. Where they will go? They will go with the effluent stream, they will be going out with the outgoing stream along with them. Okay. And they will go out with exit liquid stream. Now, larger particle means particle diameter larger than dp, they hit the wall and get separated from the liquid. Okay. Now, therefore, a cut point or critical diameter of the particle is defined. Point or critical diameter of particle is defined, and that is defined this way, that dpc. So, it is denoted by the nomenclature dpc, that is the critical diameter of the particle, and this is defined as the diameter of particle that reaches half the distance between R1 and R2 within residence time theta. Okay. That means, at t is equal to 0, r is equal to R1 plus R2 by 2, and at t is equal to Tt, r is equal to R2. Therefore, the critical flow rate can be calculated with this cut point. Now, cut point diameter. What is the critical flow rate? The critical flow rate becomes, in that case, QC is omega square rho p minus rho d Pc square multiplied by V divided by 18 mu ln 2R2 divided by R1 plus R2. Okay. So, this turns out to be omega square rho p minus rho d Pc square, and volume can be replaced as pi b into R2 square minus R1 square and divided by 18 mu ln 2R2 divided by R1 plus R2. Okay. So, at this flow rate, that means at the flow rate of QC, particles with diameter greater than dpc will settle to the wall, and most of the smaller particle will remain in the liquid and they will go out with the liquid. So, at flow rate QC, particles with diameter greater than dpc, they settle to the wall. And other small particle and smaller particles. Now, what do you mean by the smaller particles? Whose diameter is less than dpc, they remain in liquid and exit with liquid. Okay. So, we can find out that the value of the particle diameter given a flow rate, what will be the typical value of the particle diameter which will be settled on the wall or separated from the liquid, and which is the diameter range that will be going out with the liquid stream. Now, let us talk about the sigma values and scaling up issues. Scaling up of centrifuge system, that is very important, because you will be conducting all the experiments in a laboratory scale centrifuge. Now, if you would like to scale it up, you have to go for the industrial level centrifuge, which are higher, which are larger in size. So, the scale up issues are very important, and for scaling up of centrifuge system, a concept of sigma value is used. Concept of sigma values are used. Okay. Now, what is the concept of sigma values? Let us look into the volumetric flow rate. Volumetric flow rate is given as QC is equal to omega square rho p minus rho dPc square V divided by 18 mu ln 2 R2 divided by R1 plus R2. Okay. Now, you okay. So, just separate these two out. So, I will be taking the geometric and the operating conditions on the right hand side, rho p minus rho dPc square divided by 18 mu multiplied by omega square times V ln 2 R2 divided by R1 plus R2. Now, R1 and R2 will be different for a larger centrifuge, volume will be different for a larger centrifuge, and of course, the RPM will be maybe separate or maybe equal. Okay. So, I will just take these two out. Now, multiply denominator and the numerator by g. So, 2g. So, it becomes 2g there, becomes 2g here, and what is this? If you remember, this value is nothing but 2 times terminal velocity due to gravity. So, this will be nothing but 2 v t g multiplied by, and this is known as a sigma. Okay. So, VTG, what is VTG? VTG is nothing but the terminal velocity under gravity, gravitational force, and what is this sigma? Sigma is nothing but omega square times V divided by 2g ln 2 R2 divided by R1 plus R2. Okay. So, sigma value contains all the operating conditions, those are required for a larger centrifuge, because the geometric parameters volume and R1 R2 will be different for 2 different centrifuge. The rotational speed may be different for 2 different centrifuge, okay, and g is of course a constant. So, one can take up a ratio of sigma values and look into the go for the scaling of options. So, we will just look into that. So, if you put the dimension of sigma, the expression is already there, omega square times pi b R2 square minus R1 square. So, this whole term is basically nothing but volume divided by 2g ln 2 R2 divided by R1 plus R2. This will be having a unit of meter square. So, sigma is a physical characteristic of centrifuge, but not a fluid particle system. So, this sigma is a physical characteristic of a centrifuge. It is not a characteristic for fluid particle system. It does not contain any property of the fluid, it does not contain mu, it does not contain rho. So, it is entirely, and it does not contain the particle also, it does not contain the radius of the diameter of the particle. All these fluid particle characterization, that means diameter and density, viscosity, they will be appearing in the VTG, that the terminal velocity under gravity, and this sigma value is nothing but the characteristic of the centrifuge. Okay. So, that is the difference between the two. So, physical interpretation of sigma is very important. What is the physical interpretation? Sigma, if you remember, sigma has unit of area. It means it is area in meter square, okay, of a gravitational settler What is a gravitational settler? Gravitational settler is nothing but a tank where you just put the material slurry and the solid particles will deposit or settle by under gravity, and the terminal velocity is given by Vtg. Okay. So, sigma is the area in meter square of a gravitational settler that will leave same sedimentation characteristic as the centrifuge at the same feed rate. So, basically it gives an idea how this is compared with a gravity settler, okay, because gravity settler is very common. So, it gives the area under which the sedimentation characteristic is almost equal or easily understandable if you talk about a gravity settler, because it is easier to understand gravity settling method compared to centrifugal separation process. So, therefore, in order to scaling up, what we will do, we will try to maintain the same terminal velocity under gravity, same terminal velocity. So, we would like to maintain same terminal velocity of a gravity settler Tg, Vtg. Okay. So, Vtg for system 1 should be equal to Vtg for system 2. Okay. That simply means Q1 by sigma 1 is equal to Q2 by sigma 2. Q1 is the flow rate of smaller centrifuge, sigma 1 is the sigma value for the smaller centrifuge, and Q2 is the flow rate of the higher centrifuge. So, it may be 10 times of Q1, and sigma 2 is the characteristic sigma values for the larger centrifuge. So, that is it. If this is dependable, if centrifugal forces between the two are within a factor of 2 from each other, that means one can use this rule for scaling up if centrifugal forces between two centrifuges are within a factor of 2. This is a thumb rule, this is a design thumb rule. That means, if the larger centrifuge will be having a centrifugal force which is slightly less than 2 or less than or equal to 2, then you can use this rule as a scaling up option. Okay. And if not, what happens? If not, one has to use Q1 E1 sigma 1 is equal to Q2 E2 sigma 2, and what are E1 and E1 and E2? These are basically the efficiency factors of the centrifuge. Centrifuges. These factors are determined experimentally. So, using this concept of sigma value, one can scale up a centrifuge from lower version to higher version, which can accommodate more flow rate and more separation will be affected. It will be, in fact, we are going to will be solving some of the problems, example problems on this. Now, next we move on to the separation of liquids. Till now, whatever we have discussed, we have talked about the separation of a slurry process, that means solid liquid system. Now, let us move on to the separation of liquids. That means we are having two liquid stream of different density. Okay. So, the schematic of a tubular centrifuge, let us draw a schematic of a tubular centrifuge. I am just writing I am drawing a symmetric part. So, this is a symmetry, the axis about which the centrifuge is rotating with a angular speed omega, and let us say this is the portion where you will be having liquid. Okay, this is a, now we will be having a header here. Okay. Fine. This is the lighter fluid. This is the heavier liquid. So, the heavier liquid will be pushed towards the wall. So, it will be heavy liquid, let us say rho h. This will be a lighter one, liquid rho l, and you are putting the feed from the bottom. Okay. And there is a separator here, that separator separates basically from the lighter to the heavier liquid, otherwise they will be mixed up. Okay. Now, let us put the dimensions. Let us say from the center, the distance, the level of the heavier liquid will be, let us say R 4, and this distance is R 3. Okay. This separation is called, let us say R 2, and this level is R 1, where is the liquid feed is going there, and let us say R 1 is the core, it is basically air core. Okay. So, in this figure, the geometry or the details are given like this. R 1 is basically the location of lighter liquid, R 2 is nothing but the liquid interface, the interface that separates the two liquids, location of liquid interface. Okay. And this part is called a weir, WEIR. Okay. So, this weir is basically separating out physically the heavier liquid and the lighter liquid. R 3 is location of weir, and R 4 is the location of heavy liquid stream or the product. Okay. So, location of interface can be calculated by a balance of pressure in the two layers. So, let us the location of interface can be calculated by doing a pressure balance between two layers. Now, the force on the fluid located at a radial location r, fluid at r is given as F c is equal to m r omega square, m omega square r, that is the mass into acceleration. Now, the differential force over a differential thickness can be expressed as differential force on differential element dr is expressed as dfc times dm omega square r. Okay, the mass containing will be dm. So, differential mass can be expressed, dm is the differential mass and differential mass can be given as dm is equal to 2 pi b r dr times rho. So, this is the volume within the differential element and rho is the density of the fluid. So, what is b? B is nothing but the height of the bowl, height of the tubular centrifuge. Now, you will be in a position to calculate the pressure force. dP is differential pressure force. What is that? Force per unit area, dFc divided by area. So, it will be omega square rho r dr, and what is A? A is nothing but 2 pi rb. Okay. Now, you can integrate this equation between r1 and r2, the pressure difference between 2 points. So, integrate between 2 points 1 and 2, you will be getting P2 minus P1 is nothing but rho omega square by 2 R2 square minus R1 square. Okay. So, equating now you can equate pressure on two sides, equate pressure over R2 to R4 and R2 to R1. If you equate these pressures, then you can get the location of the interface rho L omega square by 2 R2 square minus R1 square. Between R1 and R2 it was the lighter liquid, and rho is equal to rho H omega square by 2 R2 square minus R4 square. Between R2 and R4 it is only the heavier liquid. So, the location of the interface now you will be able to calculate location of interface now becomes R2 square becomes rho H R4 square minus rho L R1 square divided by rho H minus rho L. Now, the interface R2 must be located such that R2 is less than R3, otherwise no separation occurs between the heavy and the lighter fraction. So, this gives you an expression of location of the interface that has to be maintained, okay? And R2 must be less than R3, otherwise there will be mix up of heavier and lighter liquids, and there is no separation possible. Okay. So, that is basic principles of any centrifuge separation process, and we have discussed the principles for the slurry, that is the solid liquid system, and the liquid liquid systems, and various scale up issues as well. So, the idea is if you know in the laboratory scale that given a centrifuge, okay, its dimension etc., all operating conditions given, this is the extent of separation you are going to do. Then if you would like to scale up, you can do appropriately. Okay. So, once after doing this, let us look into some of the examples, so that the calculation procedures etc., will be clear to us. Now, I have probably around 3 problems for you. So, let us look into the first one. First example, a viscous solution containing particles with density. So, let us talk about a slurry system. Slurry system means it is a solid plus liquid system, and it has contained particle of density 1461 kg per meter cube, and it has to be, and this particle has to be clarified, removed by the centrifuge. Okay. Solution density is given, rho is 801 kg per meter cube, and viscosity of the solution viscosity is also given. Viscosity is given as mu is equal to 100 centipoise. So, it is 100 times viscous than water, and centrifuge bowl has the following dimensions. R2 is given as 0.02225 meter, and R1 is given as 0.00716 meter. Your height is given as 0.197 meter. Okay. Now, what you have to do? You have to calculate the critical particle diameter, calculate dPc such that dPc in the exit stream if n is equal to 23,000 rpm, and q is given, q is equal to 0.002832 meter cube per hour. Okay. So, you have to calculate the critical particle diameter of the largest particle, that in the exit stream. So, let us look into the solution. The solution is straightforward. You have to first you have to convert the rpm into radian per second. So, it will be 2 pi n divided by 60. So, it will be 2 pi into 23,000 divided by 60, and it turns out to be 2410 radian per second. Okay. And bowl volume can be calculated. V is equal to pi b r2 square minus r1 square, and if you put the values, this turns out to be 2.747 into 10 to the power minus 4 meter cube. Okay. The viscosity is given as 100 centipoise, that means 100 into 10 to the minus 3. So, it will be 0.1 Pascal second. Okay. So, QC you can calculate 0.002832 divided by 3600. This is given in meter cube per hour. So, you can convert into meter cube per second, 7.887 into 10 to the power minus 7 meter cube per second. So, now if you put all these values in your governing equation, in the equation of dPc, the dPc turns out to be 0.746 micron. Okay. So, put all the values in the expression. So, it turns out to be around 0.746 micron. That means, the particles of diameter 0.746 and less, they will be going out with the liquid stream, and the particles with higher diameter, a larger diameter, they will be settled on the wall, and they can be separated by this centrifuge. Okay. And you can check terminal velocity, and terminal velocity and then you can check the Reynolds number. The Reynolds number will be less than 1. That means, you are within the Stokes regime. Okay. So, I have let us move on for the next example. Example number 2. Again, I was talking about a viscous solution. It contains a particle of density 1200 kg per meter cube. It has to be clarified by the centrifuge. Okay. The solution density is given as 850 kg per meter cube. The viscosity of the solution is 80 Cp, and centrifugal bowl will be having dimension R2 is 0.02 meter and R1 is 0.01 meter. The height is given as 0.25 meter. You have to again find out the particle, critical particle diameter, given n is equal to 15,000 rpm and flow rate q is equal to 0.002 meter cube per hour. Okay. So, again you have the steps are straightforward. You have to calculate the angular velocity 2 pi n over 60, and this turns out to be 1570 radian per second. Okay. And bowel volume becomes pi b into r2 square minus r1 square. If you put the value, it turns out to be 2.355 into 10 to the minus 4 meter cube, and the flow rate is given as 0.002 meter cube by hour. So, it turns out to be 5.56 into 10 to the minus 7 meter cube per second. Okay. Now, if you put all these values in your governing equation, the equation of dPc, this turns out to be 5.56 into 10 to the minus 7 is equal to 1570 square, 1200 minus 850 into dPc square divided by 80 into 18 into 80 into 10 to the minus 3, that is mu ln 2 into 0.02 divided by 0.01 plus 0.02 multiplied by 2.355 into 10 to the power minus 4, and if you calculate dPc, dPc turns out to be 2.57 micron. So, just check the previous one, it was 0.746 micron. By changing the operating conditions and the dimensions slightly, you will be landing up with a critical particle diameter of 2.57 micron. So, there is a huge difference, that is 0.746 micron. So, that is almost 1 micron, and here you are getting around 2.5 times of that by changing the flow rate and the other operating conditions. Okay. So, this gives an idea that given the typical operating condition of a centrifuge, what is the typical diameter of the particles, those can be separated by using the centrifuge, and you know how to do the calculations. In the next class, first I will just solve one more example for scaling up of a centrifuge, and then I will move on to the next separation process, that is the chromatographic separation process. Thank you.